Today's class. So welcome to today's session. So we will continue what we have discussed in the previous class, which is about frequency response of CS amplifier. So especially we were looking at the effect of CGD and CGS, and we looked at Miller's theorem. And Miller's theorem is used to basically decompose the element which is present here between the input and output terminal as CGD. So we understood what is Miller's theorem and how we can replace the element with an impedance Z as Z1 on input side and Z2 on the output side. So let us understand this by looking at a small example. So I am considering an amplifier. Say this is an amplifier. This amplifier is having a gain of minus AV. I am considering this amplifier is having a gain of minus AV. Now, this amplifier is having an impedance which is connected in the so when I mark it as AV, the meaning is the main signal path, or the signal is actually flowing from here to here, or this is the main signal path through this amplifier block. But there is a capacitance which is present there in the feedback path, and say this capacitor is Cx. Now the question is, or what I want you guys to try here is find what is the capacitance at the input side and what is the capacitance at the output side. Even though we have written in terms of Miller's theorem we have written in terms of impedance. Now the question here is to find the capacitance at the input side and the capacitance at the output side, C in and C out. So you may have to first write what is Z1, and then you have to write Z2, and then from Z1 and Z2 you have to write C in and C out. Can you guys try this? All right. So let me tell you how to find C in so that you can try for C out. So the main signal path is here. You can see the main signal path which is through this, and this is actually the path which is the extra or the additional path which is in parallel to the main signal path. So in such case, the impedance coming at this point. So what is the impedance in the feedback path? The impedance in the feedback path is equal to, let me write the impedance as Z, and the impedance is equal to 1 by SCX. This is the impedance in the feedback path, right? So if I know that impedance, I can write the impedance coming to the input side Z1 and in output side Z2. What is Z1? Z1 is Z by 1 minus A, and Z2 is Z by 1 minus 1 by A. All right. So now can you tell me what is C in or C1? So I'll call this as C1 because in since we are writing as Z1, I'll write this as C1 and this as C2. Can I get answers in the chat box? What will be C1? So I know what is Z1, which is Z by 1 minus A. So what is C1? Yeah, it is Cx into 1 plus A. Yes, that's right, Rajat. Kirtana, it is asked to write the impedance, write the capacitance value. Yeah, so that SCX will not directly write. So let me write it here. So it is equal to Z is 1 by SCX divided by 1 minus AV is minus, so it is 1 plus AV, right? So what is this? So I can write 1 by SC1. So this can be written as Z1, the impedance is Z1. So if I want to find the capacitance at the input side, I'll write Z1 as 1 by SC1. That is equal to 1 by SCX into 1 plus AV. So if I do a comparison on LHS and RHS, we'll come to know that C1 is equal to CX into 1 plus AV. Right, this is C1. C1 is Cx into 1 plus AV. I hope this is clear. Yes. Manikandan, the answer is right. Yes, Rajat. I hope, Kirtana, you understood whatever you have written. Without S, it should be. Because we are writing the capacitance C1. All right. So in that case, can I know what is C2? Can I get answer here? C2. Okay, I'll try that here. C2 is again 1 by S Cx into yes, Laksh, Cx into 1 plus 1 by AV. Yes, that is right. It is 1 plus 1 by AV. Again, if I write this as 1 by SC2 is equal to 1 by SCx into 1 plus 1 by AV. I can write C2 as Cx into 1 plus 1 by AV. Now, if I closely look at this term of the capacitance, I can rewrite this as AV plus 1 divided by AV, right? So C2 is Cx into AV plus 1 divided by AV, or if your AV is sufficiently large, if your AV is large, 1 by AV will be actually a very small component, right? So in that case, if your 1 by AV is very small, then your C2 is approximately equal to Cx, or you can see that it is AV plus 1 by AV. So if AV is not comparable with 1, this ratio AV plus 1 by AV will be very close to 1. So I can always assume, or I can approximate C2 approximately equal to Cx. So the capacitance seen from the input side is Cx into 1 plus AV, and at the output side it is equal to Cx. I hope this is clear. If you have doubts, you can just put in the chat box. Yeah, now if this is clear, I request you guys to apply this Miller's theorem and find the equivalent capacitance of the CGD on the input side and output side and draw the new equivalent circuit. I hope I am making sense. So whatever you are seeing on the screen is the equivalent circuit of the CS amplifier. Now, since we know how to decompose CGD and to write the equivalent components on input and output side, what I'm asking you to do is find the input capacitance due to CGD and output capacitance due to CGD, and take out the CGD and draw the new equivalent circuit. Can you guys try it? So if you have doubts, please ask now. So this is the equivalent circuit, and I know this is a main signal path. So what I will do first is, this is CGS. I want to decompose the CGD and to write the equivalent on input side and output side. So I know that will be equal to CGD on the input side is equal. So I'll write it as C in. On the input side, the equivalent capacitance of CGD is CGD into 1 plus AV, and on the output side it is equal to CGD into 1 plus 1 by AV. So that is approximately equal to CGD, that I can write it as CGD itself, but on the input side it is 1 plus AV, right? But now what is this AV? Can I check with one of you, what is this AV? Anushka, can you tell me what is the voltage gain of this circuit? The main signal path gain, yes.
Yes, sir.
Yeah.
In this it will be
All right. I'll check with Kartikeya. Kartikeya?
Yes.
Yeah. Can you tell me what is the gain of this circuit? So when I am asking gain, that is a gain without the capacitance, the regular, the usual mid-frequency gain what we write.
Minus.
sir. Can I say
Yeah, please.
minus GM RD parallel RL parallel R naught?
Very good, very good. Yeah. Karthik, I hope you also had the same answer, right? minus Gm into R naught parallel Rd parallel RL, that is right. Or in short, I can just write this as minus Gm into,
Yes.
yeah, okay, RL dash. Just I am putting this for the ease here. Otherwise, I need to write this again and again, right? So this R naught parallel Rd parallel RL is considered as just RL dash. Now, what is your C in? So C in is equal to CGD into 1 plus GM into RL dash, and your C out is equal to CGD itself. So what I'll do here is I'll just remove the CGD and I'll draw the equivalent of that. So I'll use a new color here. So on the input side I have this capacitance, and what is the capacitance value? This is equal to CGD into 1 plus GM into RL dash. Similarly on the output side, that is CGD itself, right? Now why am I doing this? So I am decomposing the element which is present from input to output on the I'm decomposing the element which is present here in this form to a grounded impedance or the grounded capacitance on input and output side, and this is actually an approximation, right? Because we are applying Miller's theorem and we are approximating the capacitance on input and output side for the ease of analysis, right? This is for the ease of analysis, and the results will be almost same. That is why we are actually taking this approximation and doing it. The results will be same, and this will actually give you this is easy to analyze, and also this is easy to actually find the cutoff frequency that we are going to just see. All right, so if you have doubts in this, you can ask me now. Otherwise, I'll go to a question and we'll solve the high frequency response of CS amplifier. If this is clear, can I get a response in the chat box? Akram, are you there?
Yes, sir.
All right, so is this clear for you?
Yes, sir. Clear.
Okay, all right. So let's go to the next question. So this is a question. So you can solve this along with me. Um, so in the MOSFET amplifier circuit, determine ID, GM, and mid frequency gain. So these things we already we have done this in unit 1. So now this is a full question. So we'll start. So now at the end of third unit, whenever a MOSFET circuit is given, you will be able to do DC analysis, you will be able to do AC analysis, plus you can also explore on the frequency response of the amplifier. That is what we are going to do with this numerical. So this cover the entire concepts what we have done in unit 1 and in unit 3 for MOSFET. IDGM and mid frequency gain. Sometimes mid frequency gain will be denoted as AM. The notation may change from literature, from textbooks to textbooks, but just I am just using the notation as AM, mid frequency gain. Right. So these three things need to be obtained. Also, the question is to determine the cutoff frequencies. So I'll explain what is the cutoff frequency. It is FL1, it is written as FL1, FL2 and FLS. I'll just write it as FLCC1, FLCC2 and FLCS. So this means these cutoff frequencies are basically determined by the coupling capacitors. That is why I just wrote CC1, which is on the input side, CC2 on the output side, and CS the bypass capacitor. So due to CC1, CC2 and CS. Now given that CGS is having a value of 1 picofarad, if CGS is 1 picofarad and if CGD is equal to 0.2 picofarad, question is to calculate the unity gain frequency, of the transistor So calculate the unity gain frequency of the transistor. Also determine the upper cutoff frequencies I'll write it as FHI and FHO due to input and output capacitance. One more component is also obtain the 3 dB bandwidth of the amplifier. All right. So I'll give you the circuit diagram and then I'll explain what all things to be obtained and how we can proceed. This is your circuit. The values are, this is 30 mega, 10 mega, 4.7 kilo, 2 kilo, this is 10 kilo, all right, all the component values are given. And the additional information regarding the transistor, its threshold is 2, its Kn dash W by L, which is mu and Cox W by L, is given as 0.5 milliamps per volt square. Early voltage is given as 100 volts, right? So this is the circuit, the question given. Now I hope like I don't know how many of you understood the question. So let us look at the question in very detail. The first thing is in the MOSFET amplifier circuit is given and this VDD is 24. The first thing is you are asked to find the ID and GM. Yeah, I'll just write R naught also because we have VA. So ID, GM and R naught, right? So the first thing is you have to find the DC current and the small signal parameters. This is basically a DC analysis. You have to go for, I hope you remember, we will take only the biasing part and you will find what is ID. That is the first thing. So with the ID value, you can find GM and R naught, which are the small signal parameters. Then you can actually go for mid frequency gain of the circuit. So for that, you have to draw the equivalent circuit. Now after that, something is asked. Determine the cutoff frequencies, FL, CC1, CC2, and CS. Right. So we know that, or in the previous classes, we have looked at the frequency response, where I said that. So this is a frequency response. Now your gain will fall at low frequency, and the components which are responsible for this fall in gain is the coupling capacitor CC1, CC2, and CS, right? So all these three will actually introduce a cutoff frequency that we will derive it very shortly. What is the cutoff frequency for CC1, CC2, and CS, right? And similarly, so the low frequency, it is the coupling capacitors and the bypass capacitors are responsible. Similarly, at the high frequency, you have the parasitic capacitance, which are the responsible element. But look at this question. I hope this part is clear. I'll tell you how to evaluate this cutoff frequencies due to the coupling capacitors. Now after that, it is given that CJs is 1 pico, CGD is 0.2 pico, and then they asked to find the unity gain frequency, which we know that which is FT. We have the formula. So already GM is there, CGS value is there, so you can find what is FT. Then the last part is find the upper cutoff frequency FHI and FHO due to input and output capacitance. The meaning is, before finding the input and output cutoff frequencies at the upper cutoff frequencies, you have to draw the equivalent circuit. And for CGD, we have to apply Miller's theorem, break the components into the capacitance in input and output side, and then you have to find the cutoff frequency. I'll be explaining this in detail. And finally, we have to find the 3 dB bandwidth of the amplifier. So basically, bandwidth is determined by bandwidth is a difference between the higher and lower cutoff frequency. So now at the higher side, there are two capacitors which is deciding the cutoff frequency, and the low frequency side there are three capacitors which is deciding the cutoff frequency. So when we consider bandwidth, we will consider the smallest of the cutoff frequency on the higher side and the largest of the cutoff frequency on the lower side. So that will give you the suitable bandwidth of the amplifier. So anyway, I'll explain this in detail. So so if you are clear with this, I'll request you to start solving it and find the drain current, GM and small signal gain of this circuit. So can I get answers? Yeah, I'll wait for 2 minutes to get the value of ID. So I'll not solve for those things. You can solve. I think you are now experts in solving these kind of questions. Take only the biasing part and you can solve it. Or what I'll do, yeah, ID is 1 milliamps. Very good, Manjunath. Yeah, it is 1 milliamps. So what I'll do here, I'll just give you the values. You can take it out and you can solve it little later, because anyway these things you know. ID is 1 milliamps. Any answer for GM? GM is also 1 milliamps per volt. That is GM. Now what is mid frequency gain of this circuit? So what is mid frequency gain AM? I can write this AM as minus GM into R0 parallel RD parallel RL. Right, this is mid frequency gain, and that is equal to, yeah, so here actually you can find two things. One is, so let me mark this as V out and this as V in and this as V signal. So we will take this AM, or this is your V out by V in, and if I write V out by V signal, the same thing, minus GM into R0 parallel RD parallel RL into, you will have this component which is ten mega parallel 30 mega divided by 10 mega parallel to 30 mega plus 100k. Right, this voltage division is also there because this is V in and this is V signal. So in between there is a voltage division happening. So that also you need to take care. So I'll just give you the answers here now, and there will not be much difference. This is minus 3.1 and this will be slightly smaller, which is minus 3.06. You can verify the answers. This is the gain of the circuit. All right. Now, so the next thing is you have to evaluate the cutoff frequencies. There are two sets of cutoff frequencies, one for low frequency and another for high frequency. So what I'll do first is I'll draw the equivalent circuit, or I'll just draw the low frequency response. So when I say low frequency response, I will not consider the structural or the parasitic capacitance of the circuit. So let me draw the low frequency response. So first I have to draw the equivalent circuit of MOSFET, which is GM into VGS when there is a VGS voltage applied here. Now R0 is there, so I have to add R0. Right, this is the equivalent circuit of MOSFET. Now I have to complete with the given equivalent circuit. So emitter node, since there is a capacitor, this 2K will be bypassed. On the base side there is 30 mega and 10 mega. So I'll just mark it as R1 parallel R2. Then here I have the coupling capacitor CC1. Then the 100 kilo ohm resistance, which is called as R signal, and here is the input signal coming, which is V signal. Right. Okay. Yeah, I need to include the capacitance, right? So I have to draw this. This is 2K. Only in mid frequency this is acting as short. So now I need to consider this. This is RS and this is CS. Similarly, on the output side, I have RD connected here. You can see that RD is here. This is RD, and from that point you have a capacitor and then RL. So RD is here, then the capacitor CC2, and then RL here. And this is V out. I hope this equivalent circuit is clear. If this is clear, can I get a response in the chat box? What I have done is, it is as same as what we have done for the mid frequency gain or the regular analysis. The only thing, or the only extra thing is, I did not assume that the capacitors are short. Rather, since it is low frequency, the capacitors are not short. That we already considered here. At low frequency, the capacitors, at very low frequency, capacitors are open, right? And both capacitors are open at very low frequency. Low frequency, both are open. But I need to find the cutoff frequency by considering the coupling capacitors. That is why I have included coupling capacitors there. Now, when I go for high frequency, both are acting as short, but the effect or the circuit will be affected only by the short circuit of the parasitic capacitance. Similarly, even though here both capacitors are open, the structural and as well as the coupling capacitors are open, the coupling capacitors or the bypass capacitors are really affecting the circuit. That is why I am considering only the CC1, CC2 and CS in this low frequency response. I hope this is clear. If it is not clear, please ask. Okay. Now, as per the question, we are supposed to find the cutoff frequencies. Now, how will I find the cutoff frequency here is, so there is a shortcut. Actually, what I can do is I can derive the cutoff frequency by considering this part, writing the transfer function of this part, and then I can derive the cutoff frequency. Similarly, for this side as well as this side, that is a lengthy process. So what I'll do here is I'm just giving a shortcut to find the cutoff frequency. The shortcut is like this. Now, if I want to find, say, I am writing FL1, which is the cutoff frequency due to CC1, right? So I will write this FL1 as I know frequency can be written as 1 by 2 pi R into C, where C is this capacitance itself, CC1, and R has to be estimated by, R is actually the sum of the resistance connected at both ends of the capacitor. So if we can see CC1, one end the resistance connected is R signal. So at that time we will not consider the signal. We'll assume that the signal is short. So so if you look at CC1, it is something like this. You have R signal on this side, and you have R1 parallel R2 on the other side. So if I want to write the cutoff frequency of due to this capacitor CC1, the shortcut method is I can write this as FL1 is equal to 1 by 2 pi into CC1 into the sum of the resistance connected across the capacitor. So one is R signal from one end to ground, and the other one is R1 parallel R2. So I will write it here as R signal plus, sorry, I'll use the same color, R signal plus R1 parallel to R2 into CC1. So this is the cutoff frequency due to L1. So what I have done here is, to find the cutoff frequency due to a capacitor, I should write it as 1 by 2 pi R into C, that specific capacitor. Now that R is the sum of the resistance connected across the capacitor. So you can see for CC1, I can see R signal on left side and R1 parallel R2 on the right side. I hope this is clear. Now, if this is FL1, can you guys tell me what is FL2? FL2 is actually due to CC2. So what is FL2? Can I ask to someone? Laksh, can you tell me what is FL2?
Yes, sir.
Yeah.
Two. So 1 by 2 pi CC1 times R.
CC1 is done, right?
Oh, sorry. 1 by 2 pi CC2 into
Yeah, so we have to look at the, yeah, I got it, Laksh. So we
Yes.
have to look at the resistance connected across the capacitor. Now, whenever we do analysis, we'll assume, so when I am writing for CC1, I'll assume that the other capacitors are short. I'll consider only one capacitor at a time. So now when I write for CC2, I'll assume that the other capacitors are short. So in that case, I can write the CC2 as, let me write it here itself. FL2 can be written as 1 by, this is actually a shortcut method I'm telling. We can derive the same thing. So 2 pi into, one side you have R0 parallel to RD. On the other side I have RL into CC2. Is this clear? FL2 is 1 by 2 pi into, let me write it in the next page. So I'll take CC2, this is CC2, and I'll write the resistances here. This is RD and this is R0. On the right side I have RL. So this FL2 can be written as 1 by 2 pi into R0 parallel to RD plus RL into CC2. Is this clear? Okay. So similarly, yeah, now this FL due to CS is a little tricky. So can you tell me what is FLCS, or we'll write it as FLS. What is FLS? Can anyone give a try? Okay, so what I need to do, FLS is 1 by 2 pi into the resistance connected across the capacitor into sum of the resistance connected across capacitor into CS. Now, if you look at this capacitor, this is a grounded capacitor. So at the one end, nothing is connected. At the other end, you have the resistance. What is the resistance seen down? It is RS. What is the resistance seen up? Looking into the source, the resistance seen is actually 1 by GM. So I can write this as 1 by GM parallel to RS, or let me write that again here. So this is the CS capacitance and this is the RS resistance. Now towards this side, you can, it is a source of the transistor, so the resistance seen is 1 by GM. So when I write it as FLS, I can write this as 1 by 2 pi into RS parallel to 1 by GM into CS. Is this clear? Can I get response in the chat box? Yeah, if you have doubts, please ask. So this is all about low frequency response. We understood how to write FL1, FL2 and FLCS. So the basic idea is to write FL1, I should write 1 by 2 pi CC1 into sum of the resistance connected across the capacitor. So here it is R signal plus R1 parallel to R2. So whenever whenever we need to find the resistance across the capacitor, if there is a signal source, we'll assume it as short, and all the other capacitors will assume it as short. Yeah, okay, that is a good question, Subramanian. Yes. So looking into source, the resistance, actual resistance is 1 by GM parallel to R0, depending on 1 by GM parallel to R0, even it is more, if you remember, we have done, yeah, in this case I have just neglected it. You can take it as 1 by GM parallel to R0 also. If you remember, the resistance looking into emitter, in the very simplest case, I can assume it as 1 by GM, right? But now, depending on the value of RD, we need to consider it as R0 plus RD by that expression also, in whatever we derived in the common gate case, right? So we can take the entire resistance there, but in this case, taking 1 by GM itself is sufficient because your R0 is the R0 value is typically high. Now we can just calculate that. Your GM is 1 milliamps, right? So your 1 by GM in this case is 1 kilo, and what is your R0? R0 is coming as 100 kilo. So it is 1 kilo parallel to 100 kilo, which is very close to 1 kilo. That is the reason why I just neglected. You can take it in the expression, you can write it as R0 also.
So,
Yeah, yes.
so if R0 is infinite in a particular case, Then will we include RD in the equation or not, sir?
No, RD will not come in the equation. No, how RD is coming to in the equation at all? You are asking
Okay.
about FLS, right?
Yes, yes, sir. Yeah, I
Yeah,
got
so
that.
FLS is this point. So look, the impedance seen from here. So that is anyway it will be 1 by GM. But if you want to go for the accurate value depending on the resistance value of RD, still you can write, but that will be again close to 1 by GM only.
Okay.
Okay, yeah. So this is the low frequency response. Can I quickly just finish off the high frequency response also so that you can calculate and you can.
One doubt.
Yes, go ahead.
What is the formula you used for the frequency 1 by 2 pi RC? Is that the RC circuit formula?
Yeah, yes, yeah. So I sorry, I forgot to
Oh,
mention
okay.
that. So the frequencies in your RC circuit, whenever you have a resistance and capacitance element, the frequency will be determined by 1 by 2 pi RC. That I directly have. I should have derived that, so I took it directly. So say for example, you have a single RC circuit like this, where this is V in and this is V out. So how will you write the frequency? That is basically frequency is written after writing the transfer function. So we'll write V out by V in first, and from the from V out by V in only we'll go for writing the frequency, the cutoff frequency. So the cutoff frequency is generally expressed as 1 by 2 pi RC when you have an R and C element.
Okay, sir. And that could you explain that how you got FLS again for
Okay,
source
yeah,
one?
yeah. So you have the capacitor CS. Across the CS, there is an RS component, and the impedance looking into the to the source is 1 by GM approximately, isn't
Right,
it?
right. Okay, sir.
Yeah. So the what I told is when you write the resistance, it is a sum of the resistance connected across the capacitor. But now if you look at this capacitor, there is nothing connected on the other side. This side there are two resistance. One is RS and another one is 1 by GM. So I wrote it as 1 by GM parallel to RS.
Okay, got it. Thank you, sir.
Okay. Yeah. So I'll quickly just go through the high frequency response also so that you can calculate the bandwidth. So high frequency response. So this is a circuit what we have. Now in this I will just delete the CGD from here, and I will draw the component here as CGD into 1 plus GM into RL dash. Okay, now you will get a doubt what gain I should take, whether I should consider the gain from this input point to output point or from V in to V out. You should consider the gain from V in to V out, because where I am connecting the CGD, from that point to the output, that gain only should be considered. That means you should consider only V out by V in this case. This to be considered, not V out by V signal. I hope that is clear, because this is the point where you have added the given the capacitance. Right. So this is the input side, and the output side you have this capacitance which is CGD. Now here also you can see there are capacitors on the input and output side. So that is why the question says that determine the upper cutoff frequency FHI and FHO due to input and output capacitance. That means in the high frequency equivalent circuit, at the input side you have certain capacitance. So this will actually introduce an input cutoff frequency. I can call it as FHI. Similarly, at the output side also there is a capacitor and few resistors that will also give you some cutoff frequency at the output side. That can be called as FHO. Right. Now, in order to write FHI, how will I write FHI? I should know what is the total capacitance and the total resistance. The resistance should be the sum of the resistance connected across the capacitance, and the capacitance is the equivalent capacitance. Now, so I will write this as FHI can be written as 1 by 2 pi into what is the equivalent capacitance on the input side. There are two capacitors which are connected in parallel. So I can write the input capacitance C in as CGD into 1 plus GM RL dash plus CGS, because there are two capacitors connected in parallel. I just added it. Is this clear? So this is C in. Now how will I write input cutoff frequency? 1 by 2 pi C in into C in is connected here, and what is the resistance connected across this capacitance? Which is simply R signal parallel to R1 parallel to R2, because this capacitor, the input capacitor is anyway from this point to ground. This is FHI. Similarly, I have written C in here. What is C out here? C out is directly CGD. So I can write FHO as 1 by 2 pi into C out into R naught parallel RD parallel RL. This is FHO. All right. So I am just winding up here. One simple exercise for you guys is when you get time today, sometime take some 10 minutes to solve this question and verify these answers. And from then, I left to find the unity gain frequency. You have to evaluate unity gain frequency, and then you should calculate the values of the numerical values of a lower cutoff frequency with these expression FL1, FL2, and FLCS. Similarly, upper cutoff frequency with this FHI and FHO. All the component values are given for you. All right. So I'll wind up here because you have a class at 10. So if you have any questions, you can ask.